Hello dear students. So today we will look these topics of unit first. Then after that your this unit first will over, right? So the topics are what are the data warehouse measures. We will do the categorization of these measures and how these measures are computed, and we'll also look what are the multidimensional database hierarchies. So we will look the role of concept hierarchies here, right? So let's start. Now, what is measure, right? A measure is a numerical attribute of a fact, right? So there will be a numerical value that represents any performance or behavior of a business, right? So it is a numerical attribute of a fact, right? So the actual number that is associated with that numerical attribute is called variables, right? And it is relative to the dimensions, right? So a measure is determined by the combination of the members of the dimension and which is located on the facts, right? So a measure is normally an additive numerical value, right, that is used to represent any business metric, right? So you are not limited to a single measure. You can have multiple measures too, right? So if you have a fact table, there will be some multiple measures in that fact table, right? For example, if your fact table is used to track purchases internationally, suppose you want to doing the business internationally and you want to track the purchases internationally, so you must have the measures of each type of currency, right? So the measures can be a multiple, right, in numbers, right, which is associated in the fact table, right? For example, if you are building a fact table for a retail industry, right? So if you have a table that you are working for a retail industry, so you have the following measures, right, in the fact table. You can have cost, you can have list price, you can have average sale price, right? So you can have quantities sold, you can have unit price, you can have amount sold, you can have profit in your fact table if you are building a fact table for a retail industry, right? So these are the examples that that we can have the following measures which is related to a retail industry. Now we will look the type of measures that are used, right, across the dimensions. So we have three types of measures here. Number one is additive measure, right? So if you see, additive measure is that measure which can be added across all the dimensions, right? Semi-additive measures that can be added across few dimensions, right, and not with others, right? Non-additive measures that cannot be added across all dimensions, right? Now what is additive measure? Additive measure, it is the most useful measure, right, which is also called a numeric and additive, right, which is also, you can say it is also called a fully additive in OLAP terminology. OLAP means online analytical processing. We will look this OLAP in the next unit, right? So if you want to get the sales amount, right, and the order count measure, so you will use the additive measures, right? So this fully additive measures can be derived from the previously aggregated results. So it is based on the aggregated values and which can be derived from the previously aggregated results, right? No matter how the user will give the data, right? We will look this slice and dice data in our next lecture also, right? The aggregated measure will produce the correct total, right? For example, if the user requests to see the sales data broken up by month, right? So we will query to the server. The analysis server receives the query and it sums the sale amount and order count of the individual items by months, right? So it will give the result aggregated and roll up by month, right? Now if you want to see the result aggregated by the quarters, right, so the analysis server will roll up the monthly aggregated values to quarter, right? So we will look the result across all the dimensions, right? So if you can aggregate the sales amount measure across any dimension to get the correct total. So you will get the correct total, right? If the measure can be across any dimension, right? So the common aggregation task that can be done in the additive measures are, you can do sum, right? You can do you can find out minimum, you can find out max, you can find out count, you can find out distinct count, right? So these are the additive measures that can be added across all the dimensions. Suppose you want to get the result by a monthly basis, suppose you want to get the result by quarterly basis, so this can be able to get the results, right, in the correct form, right? Now, if you see the semi-additive measure, right, it is semi-additive because they can be aggregated by some dimensions, but not by others. For example, if you see the inventory closing balance measure, which is example of semi-additive measures, right? That's because the product inventory balance can be summed across the product dimension, right? It cannot be summed across the date dimension, right? So for the clear understanding, we have this inventory fact table, we have the product, right? We have product A, we have product B, and we have total by product, right? So in March 1st, we have 10 products. In March, for product B, we have 20 products and total is 30. And in March 2nd, we have 15 product and 25 product of product B and total is 40. Then total we are getting is 25, 45 and 70. And if you see the ending balances for the requested cutoff date period, which is available in bracket, that is 15, 25 and 40 is the ending balance, right? If you see the fact table, which stores the closing product quantity at the end of each day. If you want to aggregate the product quantity over the product dimension, right, it produces the correct result, right? Means it produces 30 here and it produces 40 here, right? If you see the dimension across the product, right? So it is giving the correct total, right? If you want to aggregate the product quantity measure over time, right, it is meaningless and wrong, right? So what we really need, we really the ending balance, right, for the requested cutoff date, which is in the bold, right? If you see if you go to these dimensions, right, in the time dimension we are getting 25, 45 and 70. So these values are meaningless. So what we want, uh, we want the ending balances for the requested cutoff date. So the ending balances are 15, 25 and 40. So if the user had requested to see the product quantities for product A, right, so this is the product A, right, spanning two subsequent dates, that is March 1st and March 2nd, right? So the total product quantity should be here is 15, right, which is the ending balances for the request cutoff date period, right? So some measures are created only by some dimension, right? It cannot be created in the another dimension, right? So this is called semi-additive measures. Now the third type of measure is non-additive measure, right? Uh, this non-additive measure is a measure that should not be aggregated at all, right? So additive measure is aggregated across all the dimensions, right? Semi-additive measures is aggregated across some dimensions, but in some dimension they cannot be aggregated, right? But non-additive measures should not be aggregated across any dimension. So it cannot be meaningfully aggregated across any dimension. For example, the discount percentage of an order item, it cannot be aggregated across any dimension, right? Now the question arises that how measures are computed. So before seeing this computation, you have to first know how measures are categorized. So if there is a multidimensional point, right? In a data cube space, it can be defined by a set of dimension value pair. So for example, you have time, location and item. So this is dimension, right? And Q1, Vancouver and computer, these are the values associated with these dimensions. So these are the values, right? So a data cube measure is a numerical function that can be evaluated at each point in the data cube space. So it can be evaluated by this dimension value pair as shown in the example. So it is a set that is defined by the dimension value pair, right? So we will look some examples shortly, right? So this measure can be categorized into three types. That is, number one is distributive. Number second is algebraic, and number third is holistic. Right. So how this is organized into three categories. It is based on the kind of aggregate function you are using. Right, so it is based on the kind of aggregate function you are using. Means some aggregate function are used in distributive measure, some aggregate function are used in algebraic measure, and some aggregate function are used in holistic measure. Right. So we will look these measures one by one. Now the first one is distributive measure. So an aggregate function is distributive if it can be computed in a distributive manner, because means we have to partition our data into sets, right? Suppose the data are partitioned into n sets. Right, suppose the data are partitioned into n sets. So we have to apply the function to each partition, right, which results into n aggregate values, right? So if the result derived by applying the function to the n aggregate value is the same as that derived by applying the function into entire data set, so first we have to distribute that data set into some values, and we have to apply the function, right? For example, sum is a function, right? So sum is the example of this distributive measure. So we have, this can be computed for a data cube. We have to first partition the cube into set of subcubes, right? So cube is partitioned into subcubes, and we have to compute the sum of each subcube, right? Then we have to sum these counts obtained by each subcube. Hence the sum is a distributive aggregate function. It will sum up all the function in the subcube, and it will give you the result. So sum is a distributive aggregate function, right? So sum is a distributive aggregate function. So cube is first partitioned into set of subcubes, and we will apply the sum function in each subcube, and we will sum up these count, right? So hence sum is called the distributive aggregate function. In the same way, count, min and max are the distributive aggregated functions, right? So by if you see the count, right? So by treating the count value of each non-empty base cell as 1, right, we have to define each cell, we have to distribute each cell to its child cell, right, and we will calculate the count, right, and we will sum up these count, right, and we will sum up these count values to all the corresponding child cell, right, and we will get the result, right? So that's why this count is also distributive measure, right? So a measure is distributive if it is obtained by applying a distributive aggregate function, right? So if you define a measure which is distributive, it is obtained by applying a distributive aggregate function. So you have you must have these functions, right, like sum, right, count, min, max, right? These all are the distributive function, because first the data will be partitioned, and we will apply these function on the partition data, and then we will sum up these data, right? So this is called distributive measure. Now the second one is algebraic measure. So algebraic measure is computed by a aggregate function if it can be computed by a algebraic function with m arguments, right? Where m is the bounded positive integer, right? So for example, right? For example, we have average, right? It can be computed by, first you have to compute the sum of all the values and it is divided by count function, right? Where this sum and count both are the distributive aggregate functions. So this algebraic function is computed by this two distributive aggregate functions, right? So this can be computed like this, right? In the same way, we can show that minimum of n and maximum of n, right? Which find the n minimum and n maximum values respectively in a given set, right? In the same way, standard deviation is an algebraic aggregate function, right? A measure is a algebraic if it is obtained by applying an algebraic aggregate functions, right? So the aggregate values are used for calculating the algebraic functions, right? Now the third one is holistic, right? Holistic means if an aggregate function having no constant bound on the storage side that is needed to describe a subaggregate, which means there does not exist any algebraic function with m arguments where m is a constant, right? That characterize the computation. So the examples are median. You have to find the median value. Mode means the most frequent value. If you want if you want to find out rank is also holistic aggregate function. So a measure is holistic if it is obtained by applying a holistic aggregate functions. So these functions are median, mode, and rank, right? uh, Now next we will have the role of concept hierarchies, which means it is applied to dimensions. So a concept hierarchy is a sequence of mapping that is done from a set of low level concept to higher level concept, right? For example, if you consider a concept hierarchy of dimension location, right? So first we will look the city values for that location, right? So we will give the city values. Then after that, the city values belongs to which states or province, we will give that value, right? Then this state value is mapped into country, we will give the country values to which they belong. Then we will give the more generalized way that how these mapping can be done on the based on hierarchy, that is from the lower level to higher level, that is from city to country, right? In the same way, if you want to organize price by defining its ranges, that is the price is inexpensive, that the price is moderately priced, then price is expensive, we will define the concept hierarchy for this price also, right? So the concept hierarchy may be provided manually by system users, or it can be provided by domain experts, or it can be provided by knowledge engineers, or it may be automatically generated, that is based on the statistical analysis and data distribution, right? So this is a diagram of the concept hierarchy of dimension location, right? So location is dimension, right? uh, so due to this space limitations in the diagram, will not showing all the nodes in the hierarchy, right? So first it is categorized into lower level, that is city, right? Then it is categorized into province or state, right? Then it goes to the higher level, that is to the country, and it also goes to a higher level, that is all, right? So all, so this is the country, Canada and USA. Then it is divided into province and state. Then it is divided into city, means British Columbia includes these cities, right? This include these cities, New York include these cities, right? This include these cities, some more cities are there, right? So we can draw this concept hierarchy, that is from the lower level to the higher level, right? So if you see the second diagram, this is the lattice structure of the attributes in warehouse dimension. That is, it is the hierarchy of location. That is, street goes into the higher level, that is city. Then city goes to the higher level, that is state or province. That state or province goes to the higher level, that is in the country, right? Then second one is the lattice for time. Days can be divided into the higher category, that is month or week. Week can be divided into year. This month can be divided into quarter, and quarter can be divided into year. So this is the lattice for time. In the same way, you can draw the concept hierarchy of price attribute. So if we have a attribute price, you can draw the concept hierarchy of price attribute. That is $0 to $1,000. You can divide this higher level to the lower level, right? And this lower level 0 to $200 is further divided into 0 to 100 and 100 to 200, 200 to 300 and 300 to 400, 400 to 500 and 500 to 600. In the same way, you can draw the concept hierarchy, which goes from lower level in the bottom and higher level above the lower level, right? So this is the concept of hierarchy, right, which is done across the dimension, right? That is the location or the time or the price. You can choose any attribute, you can choose any dimension which is in the which is having some values, right? So it is also having the dimension value pair, right? So that's all for this lecture. Thank you.